Hi, my name is Manish Gupta, and in this video, I'm going to talk about the Kimi K2 model, which has been very recently launched. So what's new about the Kimi K2 models, right? Why are we talking about them? Well, they are large language models for agentic intelligence. Now, when I mean agentic intelligence, an agent is basically something that can autonomously perceive, do planning, do reasoning, and take actions within complex and dynamic environments, right? So in terms of planning, it can do long-term planning. In terms of reasoning, it can do multi-step reasoning. And in terms of actions, it can basically do tool use, right? So in some ways, agents can work in dynamic environments, which basically means that they can, learn from static human written text, and but then also have superhuman capabilities because they can explore, exploit, and therefore act in an optimal way in dynamic environments. Right. So Kimi K2 is basically a mixture of expert-based models. The model is basically 32 billion parameters, activated parameters, while the overall number of parameters are about 1 trillion. Okay. It basically uses a special optimizer called as the MuonClip optimizer. Now, which is a variant of the Muon optimizer with a QK query key normalization or query key clip technique to make the training more stable. Right. Now, the MuonClip optimizer is basically focused on making sure that it can make the best use of every pre-training token. So it optimizes for token efficiency. The models have been pre-trained on 15.5 trillion tokens. And because of the training stability, thanks to the MuonClip optimizer, there has been, they basically show that there is no loss spike. So besides pre-training, the model has been post-trained as well. So there are two stages, supervised fine-tuning and RL. Supervised fine-tuning is basically done using large-scale agentic data, which is synthesized so as to create diverse tools, agents, tasks, and also multi-turn dialogues, also called as trajectories. We'll talk in detail about the pre-training data later. Okay. The second part of post-training is reinforcement learning, which is basically done in two ways. So using verifiable rewards as well as using a self-critique based reward mechanism. So where the model itself acts as a critique as well. Right? So the model architecture basically is more or less the same as DeepSeek V3. It also has 61 layers as DeepSeek V3, but the number of parameters, total parameters are more than DeepSeek V3, 1.04 trillion, as I mentioned, right? However, the activated parameters are lesser, so 32.6 billion parameters. The number of experts have been increased by 50%. So there are 384 experts. In fact, they observed using what we call a sparsity scaling law that increasing the total number of experts, which is 384, actually leads to much better results compared to using lesser number of total experts. However, the experts activated per token remain to be 8, while the shared experts are just 1. So they use the same mixture of experts architecture as in DeepSeek V3, where there is 1 shared expert and then 8 experts are basically chosen out of 384 possible total experts. The number of attention heads has been decreased from 128 to 64 because they observed that if you have larger number of attention heads, basically as the context length increases, number of attention heads can actually lead to significant inference overhead. And but then they don't lead to as much validation loss reduction while training, and therefore they reduce the number of attention heads. The number of dense layers are 1 in Kimi K2, and that's that. The models have been trained using the multi-head latent attention, which is also the attention mechanism used in DeepSeek V3. The models have been trained on a cluster of H800 GPUs. They don't really mention exactly how many GPUs, but these GPUs are interesting. Each H800 node actually contains 8 GPUs, each with 2 TB RAM. So that's quite some RAM, right? The model training has been done using 16-way pipeline parallelism, 16-way expert parallelism, and also 0-1 data parallelism, as is typically done for any large-scale training. Right. Let's talk a little bit in detail about this MuonClip optimizer. So MuonClip optimizer, as I mentioned, basically is derived from Muon. Muon has been shown to be a better optimizer compared to ADAM-W in terms of the validation loss reduction that can be obtained. However, if you scale up Muon training to much larger number of tokens, it causes, I mean, in their case, they basically use 15.5 trillion tokens, right? So scaling up Muon training actually causes training instability because of exploding attention logits, right? So what are attention logits? I'll quickly talk about attention logits on the right side, but they just explode. So therefore, what they do is to basically do normalization of these attention logits using QK-norm. QK-norm, query key normalization, is typically very straightforward for multi-head attention, but for multi-head latent attention, which is what is used in DeepSeek v3 and therefore in their models as well, adapting adapting QK-norm for MLA is not very straightforward, and let's talk about it on the right side. Right. But as you can see, using MuonClip, the training is very, very smooth. This is actual training without any extra smoothing applied to it, right? The loss variation, validation loss variation. And as you can see, there is no random spikes appearing anywhere here, right? So what are these equations? Well, they talk about the normalization that is done, the QK normalization in the MuonClip optimizer. Let's look at it one by one. So the first line is basically the standard query key value computation from the input X using the weight matrices for each of those heads. So for a head H, this is how you would write the standard QKV computation. And the standard, attention computation is done like that. You compute the similarity between queries and keys, and then normalize that, apply softmax, multiplier values, get the output. Right now, to be able to, so basically, this is the attention logits that we are talking about, that they can explode, and therefore it is important to normalize them. And the way the normalization is done is basically you take a batch of instances B, and for those instances B, you basically compute the max QK value across all the heads. So you basically look at all the heads, H equal to 1 to H, and you take every pair I comma J, and you basically figure out the max logit value. And that max value basically is used for normalization purposes. How is it normalized? Well, the way it is normalized is as follows. You basically take the WQ matrix for every head. So every head is normalized. Okay, so even if that particular head does not really lead to exploding attention logits, it's still normalized in the standard QK norm. You take the attention weight matrix for the queries and for the keys, and you multiply them by gamma raised to alpha. Now, obviously, gamma has to depend on this max QK value, right? So essentially, the gamma is calculated as min over 1 comma gamma divided by or tau divided by S max, where S max is basically this maximum across all heads, right? So that's that. So that's basically that. However, first of all, these folks basically realize that, hey, why should you unnecessarily normalize those attention logits for those heads where the attention logits are not very large anyway? So therefore, what they do is to basically compute this gamma in a head-specific manner. So rather than basically just using S max, which is maximum across all heads, they basically compute this gamma H in a head-specific manner. And second, well, they do not materialize all of these keys and keys and queries in MLA attention, and therefore, the way that you would use these gammas has to be done in a more in a slightly different manner. The way this is done is as follows. So so the MLA attention was introduced in DeepSeek. So in MLA attention, you basically have latent representations for queries and keys. So the latent head-specific components are what are normalized, and the shared components are not normalized. So therefore, you see this QC and KC, well, they are head-specific components, and they are each scaled by this gamma H, for the appropriate head. Similarly, QR, which is head-specific rotary embedding, that is also scaled by gamma H, right? However, KR, which is the shared rotary, is basically left untouched. It's not basically scaled. Okay, so that's how the MuonClip optimizer works. Now, MuonClip optimizer also has a second degree momentum and so on, and it also has a component to adjust to the RMS of the Adam W. So more details are there in the paper, but this particular part, the QK normalization, considering the MLA attention, is novel in MuonClip optimizer. Okay. So further, how are the Kimi K2 models pre-trained? Well, they are pre-trained using a whole bunch of synthetic data generation. So to improve on the token efficiency, what is token efficiency? Well, how much improvement can you get in the model per token which is consumed during pre-training, right? So typically, the way people improve the token efficiency is to increase the token utility. That is basically they repeat the exposure of the token several times. You do several epochs of the same pre-training data, but that can cause overfitting. And therefore, these guys basically come up with a paraphrasing way of improving the token efficiency. So they take the same data set and then paraphrase it in various ways. So for knowledge intensive tasks, their data set is paraphrased using style and perspective diverse prompting. So they prompt larger models so as to basically get paraphrases such that the same text is written with a different style and different perspectives. Right? Since their inputs can be very long, but the paraphrasing model may basically, the rephrasing model may not take so large inputs. Therefore, what they do is something called as chunk-wise autoregressive rephrasing. So what they do is to take the full input and then they divide it, split it into multiple parts, 256 tokens, for example, right? And then they use the rephrasing or the rewriting model so as to rewrite each of these parts separately. Now, while rewriting one part, they make sure that they actually use the rephrased output as additional context, right? So therefore, this is basically chunk-wise rephrasing because you're rephrasing chunk by chunk of 256 tokens, but it's also autoregressive in some ways because you're using the previous chunk, previous rephrased chunk as an extra context, right? The third thing that they do while rephrasing, what can happen is that rephrased text may be very different from the original text. So therefore, they basically have some fidelity verification to ensure that the rephrased text actually semantically aligns with the original text. Okay. So that's for knowledge intensive tasks. Now, data set math kind of data is basically rephrased in a different way. They rephrase high quality math documents into a learning note style kind of format. So that essentially obviously augments to the original data set and therefore leads to improved token efficiency. They also translate. So translation is also another way of rephrasing, and they translate important high quality math documents from other languages into English. Okay. Now, another interesting part about their pre-training is activation reduction. So although they use machines with very high RAM, but their batch size is very high, and therefore, they do not have enough GPU space so as to save all the activations. So they use 3 different strategies to handle that. One, they do selective recomputation, so they don't store everything. In fact, they basically recompute some things as and when they are required. Right? They also use FP8 storage for insensitive activations, thereby saving space by quantization. And then they also do activation CPU offload. So there is a process which continuously keeps monitoring what can go to CPU. So they essentially also offload some of those things to CPU. So most of the pre-training is actually done with a max sequence length of 4K tokens, but then in the last few, last part of the pre-training, they basically resort to 32K sized inputs, and then at the end, they basically used the popular yarn technique to increase the max sequence length of their models to 128. So now, how are the Kimi K2 models post-trained? Well, they're post-trained using 2 main stages, supervised fine-tuning and reinforcement learning. In supervised fine-tuning, the idea is to basically use data sets with high prompt diversity and high response quality for fine-tuning. Now, they obtain this fine-tuning data from several sources using some of which uses human annotation, some of which uses prompt engineering, generating synthetic data, and obviously also has some human verification. Right? So for making the model learn agentic kind of tasks, they basically generate synthetic data and also use real data. So in terms of real data, they basically obtain 3,000 plus real MCP tools, model context protocol tools from GitHub repos. Plus they generate 20K synthetic tools. So basically the way they create this large scale agentic data is to basically take MCP tools from GitHub and then get around 3,000 definitions of MCP tools. They also generate synthetic tools across multiple domains. So for a variety of domains, they basically come up with various applications in those domains and ask large models to generate synthetic tool specifications. Right. So these synthetic tool specifications are combined with some synthetic system prompts so as to generate definitions of these agents. And then, tasks are defined for these agents with appropriate rubrics, appropriate metrics, which can indicate whether these agents have been able to successfully complete those tasks or not. So this is how overall, they synthesize their tool specifications, agents, and tasks for for large-scale agent tool use learning. Right? Now, besides these tasks and agents, they also synthetically generate interactions, multi-turn interactions with the simulated users. So this is basically multi-turn trajectory generation. And the way they do that is basically they use LLMs to generate user personas, which can indicate the style and the personality associated with any user. And then they also generate multi-turn dialogues with agents. So these dialogues involve user turns and agent turns, where the agent basically makes use of a tool simulator, which is stateful in nature and which basically can execute several tools that it has access to. And then provide realistic feedback via the agent to the user, and therefore interact with the user in multi-turn kind of settings. Right. So and again, I mean, these interactions, they have a judge agent to basically evaluate the quality of these multi-turn dialogues, and then they keep only high quality ones. Now, besides using the synthetic data as multi-turn interaction data, they also use hybrid. They also use real-world multi-turn data, where they get this real-world multi-turn interaction data from code execution development environments. Okay. So that's about supervised fine-tuning. Now, they also do reinforcement learning, and they do reinforcement learning with two kinds of things: verifiable rewards and self-critique reward. So verifiable rewards include, rewards for standard tasks like mathematics, STEM, and logical tasks, where there are exact answers and they can be easily verified. Solutions can be easily verified, right? Obviously, they also have coding and software engineering tasks where the solutions can be compiled and executed so as to verify if they are correct or not. Verifiable rewards are also available for complex instruction following. And then there is also a faithfulness reward that they include, which is more like a grounding reward. So basically, to ensure that the output that is generated does not contain sentences without any supporting evidence, right? So those are some of the verifiable rewards that they use for reinforcement learning. Now, for things like helpfulness, creativity, depth of reasoning, factuality, and safety, well, they don't come with objective verifiable rewards, and therefore they use the same model to act as a critique. So, and that is why they're called as self-critique rewards. Okay. Then they also have rewards around budget control. So when you use this self-critique, what happens is that the outputs turn out to be much longer. So they try to control the length of the outputs by penalizing long responses. And lastly, they have a PTX loss, which basically is a loss that is computed against very high quality data. So what they want to do is to ensure that the reinforcement learning does not navigate the model very far away from the original policy, right? Original good model. So to prevent any kind of forgetting of valuable high quality data that is encoded in the parameters of the supervised fine-tuned model, they basically involve this PTX loss. Okay, so how do these Kimi K2 models perform? Well, I mean, this is basically how the LLM Arena dashboard looks like as of today, right? As of 15th September 2025. And as you can observe, the top few models are all proprietary models. The first non-proprietary model is the Kimi K2 model. Okay, so essentially, on the LMSys Arena leaderboard, as you can see, the top one open source model is the Kimi K2 model. It's basically 8th overall, but is the best open source model which is available, right, on the LMSys Arena leaderboard. Now, Kimi K2 also establishes state of the art for several agentic capabilities. I'm not going to talk about all of them in detail here. You can look at the paper in detail, but on many agentic kind of benchmark tasks like OJBench and so on, the Kimi K2 model actually obtains state-of-the-art results much better compared to the DeepSeek V3 or Qwen 3, 235 billion, GPT 4.1, Claude 4 Opus, and so on. Right? So it is able to obtain high scores of 66.1 on tau square benchmark or ACEBench and SWE-Bench Verified and SWE-Bench Multilingual and so on. It also has very strong performance in coding, maths, and reasoning tasks. And as I mentioned on LMSys Arena leaderboard, it basically is top one open source model as of now. Both the base and the instruct models are publicly available. Quite obviously, since they are very large models, they require a lot of RAM to load. But overall, the total number of activated parameters are much smaller, just 32 billion. So that's basically that. So in summary, in this video, I talked about the Kimi K2 model, which is basically a 1 trillion parameter sized open weight mixture of experts model for agentic intelligence. They have two major interesting things going on in the pre-training time. One is the token efficient MuonClip optimizer. And the second is the 15.5 trillion token high quality data set that they obtain by doing a whole bunch of data augmentation, right? Using rephrasing. As part of clustering, they do supervised fine tuning, both using large scale synthetic, diverse domain data, but also large scale synthetic tool use data, right? And the tool use data is basically created by looking at MCP tools, but also synthetic tools derived from large language models, building agents on top of them, and then building tasks and metrics on top of them, and also multi-turn conversations. So as part of posturing, they also do reinforcement learning using both verifiable rewards and self-critic feedback. And the nice part is that Kimi K2 establishes new state-of-the-art for several agentic and reasoning benchmarks. That's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.